Well, hello everyone. Welcome. This is our latest in the series for Learn Live. Use consistency models in Azure SQL DB, Azure Cosmos DB SQL API. I'm Mark Brown. I'm a principal program manager on the Cosmos DB team, and I'm joined for this session by a good friend of mine, Chandra Dahl. Chandra, would you like to say hi?
Yes. Hey, hello everyone. Thanks, Mark. I'm Chandra Dahl, CEO of Kasten. I'm also a Microsoft MVP and RD.
It's great to have you with us. This is the first time we've ever done, I think, any kind of session or anything like this, isn't it?
Yes, sir. Exciting.
Yeah, this will be fun. This is one of my favorite topics in the whole world. Is the one we're going to talk about today. So just to get started, if you'd like to follow along, here's an AKA MS link that you can, I guess, quickly type into your browser if you want, or I guess you can snap that QR code. But then I guess you're following along in a mobile phone. I'm not sure if that makes sense, but you can you can try. I guess phones are pretty powerful these days, aren't they, Chandra?
Screenshot and use AI. That's what I do.
AI, all the things, right? So, okay. So, in addition to Chandra and I for this session, we've also got our moderator, Glenn, and I know Glenn's been introducing himself and saying hi on the chat. So, if you've got any questions during the session, feel free to pass them along, and Glenn will be happily taking your questions, and we'll even pass some on to us as well, and we can answer those live on air for you. So thank you, Glenn, for joining us. Good to see you again. Okay, so this is our session. Here is the AKAMS link if you want to follow along, and you'll see this Microsoft Learn session available up at this link here. Another reminder here as well, this session is part of a larger whole for our certification for Azure Cosmos DB. So we have a specialty certification for Cosmos DB. And you can learn more about that from here. And I encourage you to go and click on the link here, learn more about our certification, and then, best of all, consume all of the content that we've got, all of the learning and skilling content that you need to help you pass this exam is available on Microsoft Learn and also available through these Learn Live sessions. And we're nearly through all of them at this point now. So pretty soon you'll be able to watch all of these and then get yourself caught up and follow along with all the labs that we do for these here. Okay, so that's it for introductions. Let's get started. And Chandra, you want to talk us through our learning objectives for today's session?
Absolutely. So our learning objectives for today are to configure a default consistency level, because every Azure Cosmos DB account comes with a default consistency that basically works for the entire account. And then the great news, and this is what I love as an app developer, and even DBAs love this, is that you can actually change the consistency level on a per request basis. So we're going to cover both the topics quite extensively in detail today. And then don't forget, oh, sorry.
No, go ahead. Sorry.
Cool. Don't forget that this is a live interactive session. So please make sure you head over to the chat, say hi to us, and ask any questions as you might have. And is it right, Mark, that we're going to be checking the chat and hopefully try to answer questions as we go through the material?
That's right. So Glenn's going to be capturing all of the questions that people ask, and he'll handle some of those, whatever the questions are. But then some he can pass along to us, and then we can answer them live on air.
That'd be great.
Yeah. All right. I think we got all the housekeeping out of the way here. So let's get started with the introduction on this topic.
So one of the cool things about distributed database platforms is that they're no more what it used to be 10 years ago, right? When you heard, hey, we've got these two consistency levels, and here's a strong one, and here's a weak one. What I loved about Cosmos DB, and I think it used to be called Document DB at that time, many years ago, when I looked at, oh my gosh, wow, they have 5 different ways of doing consistency levels. And that's what got me really excited, because I had so many different use cases in the past. I was doing a lot of hacks. So I was like, this is cool. But by the way, maybe a lot of you might be wondering what consistency is. And if you are like me, coming from a relational database background, you might be thinking of consistency as ACID guarantees. There's a consistency in ACID. For those who don't know ACID, I think most of you do, but just wanted to make sure it's atomicity, consistency, isolation, and durability. Now, the C in ACID happens to be a completely different consistency. And I call it more like a transactional consistency where, if something goes wrong during the transaction, you don't really violate the data integrity. Now, the consistency we talk about here in terms of a distributed database is quite different. It's more to do with, let's say you have a write and you have a lot of different partitions or regions or whatever, and now you do a read. What does that really mean? Did you get the latest data? Well, the latest data or information, if you get it the moment you make a query, make a write on your read, is basically that particular kind of consistency. So isn't this, Mark, the consistency that we have in either CAP theorem or more like CAP LC theorem?
That's absolutely true, right? So this is the thing that I think a lot of relational developers, and you pointed this out quite well. This is not consistency from an ACID semantics. This is consistency because as a distributed NoSQL database, we replicate data or can replicate data to other regions, right? So you write data to one region, and then that data gets committed into that region, and then it gets replicated into other regions. Now, there's multiple reasons why you would want to replicate data to different regions. You may, I think primarily one of them is to be able to survive a regional outage, right? So we provide a higher SLA on your account if you replicate data into a secondary or more regions. And then the other reason is you may want to reduce latency for reads, right? Obviously, the closer you can get your data to your user, the faster your applications are going to perform, because if that data has to go across a wide area network, that takes time, right? And even though packets are running at the speed of light, you're still talking about many, even in some cases, hundreds of milliseconds, and sometimes even longer. You just never know. Like WANs are a flaky place. So this is what's unique, I think, about Cosmos and these consistency models, and the fact that we do this replication and then can control it with that is in all those levels. And so let's spend some time and talk about understanding each of the consistency models in here. So as Chandra mentioned, right, so this is a distributed...
Not to interject, we just got a question, what's CAP theorem? And I'm going to start, and feel free to add what you think. So CAP theorem is basically an acronym, stands for consistency, availability, and partitioning. And whenever you look at distributed programming, distributed databases, as Mark mentioned earlier, you're going to be in multiple different regions, and you're going to have data that's going to be replicated. And of course, you're going to have places where you go write. For example, I had a write region in the United States, and I wanted to be replicated in Europe, or even Australia, or East Asia, or somewhere else, right? So now in this situation, we basically get 2 out of the 3. So we could either have consistency and availability or have partitioning, right? Or we can have availability or partitioning versus consistency. So we may lose on consistency to have more availability and partitioning. And we may actually lose on, partitioning if we were to go with CA, in this case, consistency and availability. So basically think of this as a triangle where I could only pick 2 out of 3 for the most part. And for the third one, we're going to get there eventually. But the idea is that there's going to be some kind of trade-off. And then CAP LC theorem is more like CAP ELC, which basically talks about else, latency. And Mark, you want to talk about CAP LC?
Yeah, so the PAC-LC theorem is basically an addendum to the original CAP theorem that Eric Brewer devised. And what that says is that even when your network is still functioning, so in CAP theorem, you lose network connectivity, and then you have that choice, that trade-off you have to make, as Chandra mentioned. Even if things are working okay, though, there's still a secondary trade-off, and that's latency versus consistency. And so the consistency model you choose can have an impact on the latency for your application. And in fact, I've got some slides that I want to show later that kind of help illustrate this, Chandra. So for the person that's asking the question, stick around. I'm teasing you now because we've got some cool slides and some cool demos that's going to show what happens when you make specific choices for consistency in Cosmos DB. And even whether or not you replicate as well. That's another trade-off you have in there as well. So let's talk about these consistency models in here. And then we got some more stuff. And then we'll get to our exercises, which is where all the fun, all the magic happens within our exercises. So, all right. So let's get going here. And Chandra, you want to just kind of quickly name off all these? We're going to go into more detail here on the subsequent slides, but this will give people a good grounding.
Absolutely. Strong consistency. It's also called linear consistency. And really think of this as your asset guarantee, right? When it comes to a relational database, think of this as you're on one particular device or region. In this case, Cosmos DB allows you to basically have strong consistency. Means if you ever have a write and you do a read, no matter where you are, you're basically going to get the last write. So you lose nothing. So this is the strongest it gets. And that's why it's called strong consistency. Bounded staleness basically means you're always going to lag a little bit behind your writes. And you can lag either by the number of commits you have. So basically you could be, let's say, 5 or 10 commits behind, or something like you could be, behind by 5 or 10 seconds. And really the lag depends on either the time or basically the commit in versioning of your document that we're talking in this case. And then third one, session consistency, the most popular one of all the 5, I guess, because think about this as, you went on Amazon.com, you added your comment, and you were able to see it because we're going to give you session level consistency. However, if someone else basically goes to Amazon.com and looks for the comment, that comment might not be there for another, let's say, 5, 10, 15 seconds. And that's okay, because that's why we have a session consistency. There's a trade-off. The fourth one is consistent prefix. As you can see, the name automatically states, there's some kind of ordering here. And this is exactly what it is. Basically, you may be behind, but you will never be out of order in terms of consistent prefix. And the final one is eventual. Basically, you could be completely out of order. You could be doing reads, and you may be getting things completely out of order because it's the loosest consistency out there, but it's also the least expensive in terms of throughput. And that's why it's called eventual consistency.
Yep. Good. That's a good recap of them. So let's dive in, and then we're going to kind of crack these open a little more in here. So first up is we've got strong consistency. Now, as Chandra mentioned, this is linearized consistency. So when you write data into your write region in Cosmos DB, that data has to be globally committed. So if you have one region and you write data using strong consistency, it's just going to commit and it's going to behave like it normally would. Where latency begins to take effect here is if you have 2 or more regions in there. And what the effect is when you use strong consistency, that data must commit into the region where it was written. So that's going to be your primary write region. And then it must replicate and commit in every other region that you have configured for your account. Now, because those regions are some distance away from the region where it was written, you've got kind of speed of light issues at work here, right? So the data has to commit, has to get copied over a wide area network, and then it needs to commit into all of the other regions that you've got configured for the account, and then act it back to that primary region, to the service, and then it'll act back to you. So the effect of this is that when you use strong consistency, your latency is impacted if you have additional regions, and that latency will change depending on the distance to those regions. Okay, so that is strong consistency. And of course, with strong consistency, as kind of the name implies, there is no dirty reads in this. So no matter which region you read data from, whether it's the data you write or the region you write to, or any of the other read regions, that data is always going to be perfectly consistent globally. Okay, next up is bounded staleness. So Chandra, you want to talk a little bit more about this one?
Absolutely. So, take the name, bounded staleness. What does that really mean? Of course, well, I'm assuming there's going to be some kind of stale data, but it's bounded. And bounded by what? Bounded by us, basically, because we get to tell Cosmos, hey, bind it by X amount of items or versioning items or commits, or at the same time. So I'll give you an example of that. For example, let's say you are in the United States and you've got a game going on over here and you want that region to basically know all the latest data. So you could easily use bounded staleness, saying, all right, all the latest data that's coming in, every single score, people watching on their cell phones and everything could basically see that data come in really quickly. Or you could do that same with a stock market, for example, and you have all your tickers coming in. However, just because the game is here, you may have people watching this game in Europe or even Asia, right? So what you want to do is, let's keep this strong in this particular region, and bounded staleness by default for the same exact right region always gives you strong consistency. But you can say now, look, let's say 15, 20 seconds later, I'm okay with this being replicated on a completely different region, right? Because now they're going to make writes from Europe or Asia or some other place. So if you look at the numbers, basically for bounded staleness is, think of this as exactly similar to strong consistency, except reads are allowed to lag behind the writes up to a certain threshold. And what's that threshold? So for example, for a single region, the minimum value of K, as you see up there, K versions of an items lag behind the writes, that is basically 10 write operations. And T, which is the time interval lag behind the writes, is just 5 seconds. When you take multi-region accounts, the minimum value is 100,000 write operations, by the way. So this is important to understand. And then T is 300 seconds. Now, you all might be wondering, oh, wait a minute, well, that looks like a lot. That's 100,000 write operations, and that's 300 seconds, But one thing to keep in mind is that, good news is that inside the staleness window, what that means is, let's say your staleness window happens to be 100,000 write operations for K, perfectly fine. In that case, you still will get, in the same write region, strong consistency. And if you are in the same write region with clients or the read operations coming on from different regions, you'll actually get consistent prefix, which is something I'd like Mark to explain what consistent prefix means.
Okay.
Actually, the next one is session consistency.
The next one's session. But the only other thing I wanted to mention too is Chandra mentioned the single region K and T values of 5 seconds and 10 updates. And then there's a multi-region, and that goes up. Your minimum values for that is 300 seconds, so that's 5 minutes, and 100,000 updates in there. The other, so it's drastically larger, right? And the other thing that distinguishes it and all the other replica or consistency models from strong is that this is asynchronous, not synchronous, right? Because you're not globally committing into everything right when the write, as part of the write and the commit within there. And then I guess you mentioned you get strong reads for primary write region as well, so that makes sense. So you get kind of that look of strong within there, because if you're reading from the region you read, if you're reading from the region you wrote from, that makes sense, right? Your data is going to be there. Okay, so that's good. And then, okay, we talked about this as well. Yep, that's what we just talked about. Let's talk about session consistency next. So this is the default for Cosmos DB, the service. So if you don't pick anything for your consistency when you create a new account, and this is configured at the account level, by the way. So every database, every container within that account has the same consistency model. And so if you choose nothing, it's going to use session. And you may be asking, well, why did we choose session as a default consistency for Cosmos DB accounts? And there's actually a fairly common or a sensible reason for this. And that is the consistency guarantees you get from a consistency model like session is essentially kind of read your own writes, right? And that's typical for nearly every workload scenario application service wherever, right? Consider if you are in an e-commerce site and you start adding stuff to your cart, you want to be able to read back from that right. if you go back in there, right? So, or anything you read, anything you write in, you should have the expectation you should be able to read it back. And session consistency provides that sort of write guarantee. And how it does this is because of the way session consistency works. Now, session consistency is different from all the other consistency models that are available within Cosmos DB. This is what's referred to as a client consistency model, and it's not data driven. Like with Strong, it's the data itself, or bounded staleness, or any of the others. These reflect kind of the behavior of the data itself within the consistency guarantees. Session is different. It's managed, it's client centric, if you will. And how that's implemented is it uses a session token, which underneath the scenes is essentially kind of a physical address for where the data is stored, and then also an LSN or a log sequence number in there. And so when you write data, you get back that session token if you ask for it. And then when you do anything consistent or subsequent to that, you pass that session token back. And I think Chandler's going to show this off a little bit later about how that works within our SDK. But that session token is then used to check, hey, make sure that I read my latest data, because here's the token I got back when I wrote it. Okay. And so that's how that works, is that it uses this session token to pass back and forth from the service. Now, if you just use a single SDK instance, you don't have to do any of this. The SDK will manage it for you. It actually silently will keep an eye on that session token. However, if you have multiple instances of your SDK, and let's say you've got like a web farm or a middle tier that's like a whole, like a pool of VMs or other compute that's running, you can flow that session token all the way back to your end user, and then they could send that back in subsequent requests. So if you're using some kind of round robin or some other load balancer, you don't need to worry about having like sticky sessions or anything else like that to ensure that people are getting the same data. You can just flow it back and forth from the client in there. Okay, so that's enough on session. Let's talk about consistent prefix.
So think of this as a little looser than session, because you won't really see what you wrote, except you still will have a guarantee that reads will always appear in the order they are actually written in. So reads are going to lag behind the writes, and you won't have what session consistency gave you, which was basically you're able to read your own write. Other than that, you are at least rest assured that any single write that ever happened, at the global level, basically is going to come to you at the same order. So this is very important, where the order of getting anything is very, very important, right? So for example, if you're doing stock market trading, for example, right, let's just say there is even a lag or whatever, but you don't want to miss the order of who ordered first, because that could cost someone money, right? So something like that, where ordering is extremely important, this is definitely something that you may want to consider. And keep in mind, right, one of the things that in the beginning it was hard for me to understand is, just because they mean a guarantee, what does that really mean? So when Cosmos DB started, I think it was Document DB at that time, I think the guarantee was 15 milliseconds for writes and 10 milliseconds for reads. And you'll be surprised that we had a client with more than 2 billion hits on one day. And that was actually one of the record e-commerce in those years, 5 or 6 years ago. And you'll be surprised that we never had a write that was more than 11 milliseconds, given all the conditions are true for that guarantee. And we never had a read that was beyond 8 milliseconds. So when the word guarantee is used, that means that was the worst case. Now, currently, that number is only 10 milliseconds read as well as write, and that's pretty incredible. So when we look at these guarantees, right, well, the interesting part of these guarantees is that you may actually be getting a guarantee without you realizing what it is. For example, you might be paying for bounded staleness, but within the same region, write region, it happens to be actually strong consistency, right? And bounded staleness for the rest of it. Same with consistent prefix. When you have a single write region, and you may have a client, which is a read client in the same region or a different region, you're actually going to get consistent prefix there. And this also applies to multiple write regions. Regardless of you having a client or a bunch of clients, you still get consistent prefix. However, when you're writing to multiple regions for an account with multiple write regions, you'll get eventual consistency, which, Mark, do you want to talk about eventual consistency?
Yeah, sure. Before I do, though, one thing I wanted to mention, and this is something we forgot to bring up when we were talking about strong and bounded staleness, but let me back up a little bit here. There's something else you should understand about strong and bounded staleness consistency, and that is, how do we guarantee, how do we know that's the latest data? And there's actually a very simple way of doing this. Cosmos, as a NoSQL database, stores data 4 different times. So we have a 4 replica set, and anytime you write data into Cosmos DB, your data is committed into 3 out of those 4 replicas, and then the 4th one gets hydrated asynchronously in the background. Now, you write data. So you've got 3 of those 4 replicas that have your data. And this is true for strong and bounded staleness. When you issue a read against that region, it's going to read normally for a session, consistent prefix, and eventual. It's just going to read from a single replica. Okay. The difference for bounded staleness and strong is that that read is done from 2 replicas. Now, the thing with that is when you read from both those replicas, we can read the LSNs from both replicas when we read the data. And then we compare those 2 LSNs. And if they're the same, that means that we're looking at the strongest or the latest data that's been written in, right? Because that means that we've read from 2 of those 3 replicas that we wrote to. Okay, and then we return that data. If they're not the same, that means that we're reading from 1 replica that got that right and another replica that has not yet seen it. And if that happens, we return the data from the replica that has the higher LSN, because that is going to be the most recent data that was written into Cosmos at that point. The second point I want to make about this is because these reads are 2 replicas instead of 1, the RU cost, the RU per second, right, or request units per second charge for that read is double. Okay, so, or conversely, you get half the throughput on your reads because it is reading from 2 replicas versus 1. So this is important to understand. In read-heavy workloads, the cost of your reads is going to be double that unless you double that from session or weaker level of consistency. So that's all I wanted to bring up. It's an important point, and it's one that's not always immediately understood or grokked by people who are exploring our consistency models. Okay, now on to eventual. So eventual is the weakest consistency, and as the name implies, eventually all the data will be available in all the replicas everywhere. And there's no particular order in which this happens. Now, as you saw or have been listening, through our discussion through each of these consistency models, there's a trade-off happening as you go from strong all the way down to eventual. And that trade-off is on really throughput, right? With strong being the most strict, your throughput on writes is limited, right? Because you have to have your data globally replicated and committed for that data or for that write to be acknowledged and recognized back to the client. With eventual, it doesn't matter, right? It's asynchronous, first of all, just like session and consistent prefix, but it puts even fewer controls on how that data is replicated into the other regions within there. So scenarios where we see things like eventual consistency used quite often is in, like, say, IoT scenarios where you're ingesting vast quantities of telemetry or data coming from devices. You obviously want the highest amount of throughput you can get for the lowest amount of cost. And then typically in a lot of IoT scenarios, you're okay trading off having perfectly consistent data in multiple regions because you're ingesting low-level telemetry data. You're unlikely to look at it until it's like processed maybe through Stream Analytics or available in a Power BI or some other thing happening downstream where you might look at that data. So that's the last one. There was one other thing I wanted to say about, there's always so much information about these consistency models, and I want you to understand, and that's why these things are so important. One other thing to understand about bounded staleness. So this is asynchronous, right? So unlike strong, this is asynchronous. So you can go and you write your data, and then we maintain that consistency guarantee in the background. As the service approaches the window for the staleness, so if you're in a multi-region account and you're approaching that 300 seconds or that 100,000 updates, Cosmos will start putting the brakes on accepting new writes in there. And this is to allow the service and the replication engine to be able to catch up so that it can maintain that consistency guarantee, right? And this is something we have to do, right? Because the consistency guarantees are essentially prime above all else in there, right? We must honor these consistency guarantees as selected and defined in the case of bounded staleness for your app. So just another thing to keep in mind, this doesn't happen with any of the other weaker consistency models or asynchronous consistency models. It only happens with bounded staleness. But considering that the name bounded staleness implies that guarantee, we have to do something to keep it from breaking that guarantee. So that's how we do it. Okay, moving on. I think we're doing good here on time, and I hope people are getting lots of good information. Okay, so Chandra, over to you. We're going to talk about how to configure the default consistency model in the portal.
Awesome. Mark, that was a lot of really good information. And, it's interesting that over a period of time, I learned a lot of that. But the things you talked about are so important, especially when we're designing our solutions. Graces are everything. So this is really the portal, as you can see. And if you go all the way down on the left-hand side and you click the default consistency pane, you can see that all the 5 consistency levels are right here. And what I really like is, if you have some kind of, let's say for some reason you forgot what really consistent prefix means, all you got to do is click on consistent prefix, and you'll start noticing at the bottom right-hand corner that, all these regions actually start telling you how the consistency is going to change actually. So for example, right now we're at a session, and as you can see, you got North Europe as well as rights in session A, and that's what you're doing. And you'll get everything right there. And look at North Europe reads, you're going to get everything right there, right? So if you look at the red color or the blue color, everything is in order, and you're getting it exactly at the same time. Now look at the replication, which is happening in North Central US. In this case, we have session, but look what happens. The red record is basically now there's about a lag of 2, and it still is there. And then you look at the blue record, which is consistent in all the first 3 regions. And again, there's a lag of 1, and it goes to the next one. But look at the order. It's always going to be that way, right? The order is the same. Yeah, wherever we have the session consistency, we're getting it all the regions as it is. Pretty perfect. Good to know. So if you ever have any confusion whatsoever, right, come and click on these consistency models. Mark, do you mind clicking strong for a second?
That doesn't actually do anything because it's just a slide.
Sorry. That's a slide. Okay.
So, yes, I can click on it, but no, it's not going to do what you asked.
But definitely use this tool, because this is one thing that helped me visualize the consistencies in the beginning, because otherwise, you learn from your experience, but if you can visualize it, makes so much easier, your life easier. Actually, let me give an example of what I would like to do is give an example of session versus eventual, and then also, tell you how to hack it, like we did for one of our clients. So the first example is from LinkedIn, and I noticed it myself. So I went to add a job, and the moment I add a job, I don't see the job over there. So the first thing that goes in my mind is, wait a minute, so we're missing session consistency over here. And I start thinking, why would that happen? Well, simply because, how a lot of people will tell you that, hey, if you want to go do something with social media, it's completely okay for it to be eventually consistent. And that's really the benchmark of it. Like, whenever you talk about eventual consistency, your use case happens to be social media. But this is an example of a place where you may be having social media, but the jobs engine is for companies, right? That's really not like a comment. So if you had a comment, 97th comment, does it even matter? You show 96 comments or 97 comments. And if there's a 5 or 10 second lag, does anyone care? The answer is no. However, when you post a job and it doesn't get posted, you go, wait a minute, what did I do wrong, right? And I started working on it. In fact, I actually had to send an email to the support saying, look, I don't even see the job for 2 or 3 minutes, but it keeps telling me it's already posted. But there is no way I can see this on the same browser, on my mobile app, or anywhere else. And I use a Windows as well as my computer right here, and it won't work on anything, right? Took more than 5 minutes, and finally the job shows up. So that's an example where you should have had session level consistency, because right there, I would be like, okay, great, I saw it. And do I really care to get posted in 2 or 3 minutes? Probably not. Now, looking at the same exact example, we had a client that comes to us and said, look, eventual consistency happens to be the cheapest, and we pay the least amount of money, of course, right? And they're concerned about their bill. So they said, how do we get session level consistency without having to pay for it? So now this is a hack, by the way, and I'm going to give it to you. But that doesn't mean that you can use it for every single use case, because I just give you an example that there is no solution for a broad use case, right? But in this particular use case, it actually worked out really well. So in this case, they had admin tools, and they were building admin tools internally, and they wanted to do it. And really what mattered was the admins read to themselves. So what we ended up doing, I'll show you that in a second. We basically took the token, not from the session consistency. We actually created our own token. And what it would do is it would actually leave it on the UI as long as you were there, because we were using progressive web apps, and progressive web apps ends up using IndexedDB, which can basically take JSON kind of data. And we would leave it over there for the entire day, pretty much. If you need it, you won't need it for more than a few, I would say, 100 seconds there. But we left it just in case you have that versioning going on. And now you are only paying for eventual consistency, while your user interface would see that. Now, keep in mind, that would not work if the person goes from that browser to another browser or some other reason. Can it work with that another browser as long as you are doing the same PWA with the IndexedDB? Yes. But then you're going to have a problem with if the person ends up on an app or something like that. So this was a use case where it worked out, and it was twice as cheaper, I guess, and they saved some money, and it was a cool hack. But I would say use session consistency for the most part. Do not get into such issue down the line.
So it sounds like you used IndexedDB as kind of a write-through cache. Is that kind of the right kind of take on that? Am I reading that right? What you did there?
Pretty much. And since they always had this thing about that they were only using on the internal network on the same exact browser, and they even had the lockdown browser, we didn't have anything to worry about. But trust me, it's not saving the money if you're going to have to test that thing in multiple different browsers and other places, right? So it's a cool hack, but not something that I would always do.
Yeah, and that's I've had customers as well that have wanted to kind of cheat, if you will, kind of whether it's CapDem or PackLC, or try to get, I don't know, similar types of things. And I've seen similar kind of solutions to that, where they've kind of basically just cache the data on the client or close to the user as they write it in there, so that it's there for them.
Just
yeah,
to warn
it's
you,
hard
by the
to.
way.
What's
Sorry,
that?
go ahead.
No. But there's a reason why I don't see much of that, and that is it's hard, and it just adds more complexity to your solution. It's much easier just to let the service do it. That's why people just use what's available here and implement consistency as we've got available. But
Absolutely.
Yeah.
And I was going to warn you, right? What happens is that sometimes when you start doing these hacks, you get to a completely different, way of doing things, and that can mess up things for you. For example, we had a client of ours that, started doing some of this caching, and then they realized that it was not working very well. And just so you know, right, they now had to add another Redis cache to make all this happen. And what's funny is we came back a few weeks later and said, by the way, you're getting 2 to 3 milliseconds on Redis. And do you know that most of your 99 percentile of your data is coming back from Cosmos in less than 5 milliseconds? You don't even have to add something completely different. In fact, there's a lot of clients where we actually got rid of Redis completely, and we just use Cosmos, because even though the guarantee says 10 milliseconds, it's always 99% of the times it's basically 5 milliseconds, right? So I would stick with these consistency levels the way they are, because they are made for every specific purpose, but understand that you can change it on a per request basis. So don't ever be afraid of experimenting, because that's how you're going to learn a lot. Of course, just make sure your use case is probably not like what LinkedIn did. And if LinkedIn people are watching, more than happy to help you with that particular use case.
You said something that made me remember something, and that is when you're using multi-master and then writing and reading from different regions, and that when you do that kind of configuration, the only consistency you can get is eventual, basically. So there's caveats as to where the reader is and what your write configuration is, whether you're single region write or multi-region write, and where those writes happen and where those reads happen play an impact on the consistency guarantees that are provided by the service. Now, I've seen people try to do some very interesting engineering in there. I've seen people who wanted to get read your own write guarantees, multi-region, using session consistency. And so what they ended up doing is they ended up implementing, I think is it called consistent collections or something in there, where they tried to persist and share the session token, and then they would replicate that into other regions. And when I ended up looking at this, I'm like, you realize you now have the same problem now that we do, which is you have to replicate something. And now it's not us doing it. you're doing it. So I don't know why you would do that, but you can't cheat. You can't cheat cap theorem, right? Or PAC-LC. These things are always going to be what they are. And yeah, anyway, so
one of the things that worked for me is like I'll rather let Cosmos DB team handle it than me handling it, because that's less work for me and it's going to be hard to keep testing that whole thing. But I'm with you here, right? So we cannot change anything when it comes to physical laws, right? There's going to be some kind of delay, whatever it is, even if it's the fraction of speed of light. I mean, it's still going to be quite a bit for us. I mean, for me, 100 milliseconds is a lot sometimes. We do a lot of applications that are below 100 milliseconds on every single cost. But let's just be, honest that if you have something in East Asia and in the United States, well, it's going to take a couple of round trip times for them to get synchronized. And that's a problem that I would rather not solve, and that's where I can rely on Cosmos, which gives me that opportunity at a pretty amazing latency guarantee, which, I mean, I don't even know if anything else even provides. So
yeah, it's the only database in Azure that has a latency guarantee for data. And like you said, these are typically you're not waiting a whole, like an extraordinary amount of time. I mean, in some cases it's just milliseconds or maybe a few seconds. So the scenarios are kind of thin, if you will. There's not many where you would run into issues where your latency or replication are going to be causing issues. Now, not to say there's not going to be, but just keep in mind that the server's going to replicate the data as fast as it possibly can, and so in many cases, under scenarios where you're not like blasting gigabytes of data at the service all at once, the replication mechanism can work rather quickly and can work to copy and commit that data into subsequent regions, and do so pretty fast. Okay, let's keep trucking along here. So we're going to talk next about how to change the consistency model with the SDK. And I've got lots of stuff to say about this, but what I want to do is I want to show you here the way you change this. There's a couple of different places you can change this. You can change this on a per request basis. You can also change it for the entire session. Now, this code here shows you how to change it for a specific request. And so within that, you're going to have we have this class called item request options. And so what you do is you just new up a new instance of that. And then you can set this consistency level property to consistency level dot whatever consistency level you want to choose, provided that it's a weaker consistency level. You cannot, and I'll repeat, cannot increase the strength of the consistency model used when you go and override it either at the item or at the session level. Okay, so if you're using, say, session level consistency, and you want to, I don't know, you want strong consistency for this, right? You can't do it. In fact, another thing I want to point out is that consistency only applies, at least for all the others, everything except strong, only applies to the read path in here. Okay, so that's what consistency is referring to in terms of where that guarantee is made. It's on the readers that happen within there. Now with strong, that's different because it's serialized, so it impacts writers on that effect too. But the impact as well is the same as readers are impacted on here. So here is some code that shows you how to reduce the consistency model for your request within there. Now, you may ask, why would you want to do that? There's actually a good scenario for this. Let's say you've got a workload that's using a strong or bounded staleness level of consistency. And let's say at the session level. So you want to new up a new instance of the Cosmos client, and you want to ingest a whole bunch of data and do it rather quickly. If you're using strong consistency, your latency is going to be quite painful if you have to ingest a whole bunch of data and do it quickly, because it's going to have to commit either at the right region and all the other regions before coming back. So your latency is just not going to be that awesome. So you can do something like this where you can create a new instance of the SDK client, you drop it to say eventual within here, and then ingest all your data in that session with eventual consistency within the account there. And then it, of course, eventually will get consistent within there. So that's kind of a scenario for that. within there. What do we got here? So, and then here you can see, so after I've set my request options here, I'm going to do a read item async within here. And then of course, I'm going to pass the ID, the partition key, and then of course my request options here as part of that read within there. All right. What's next? Session tokens. Chandler, you want to talk a little bit about how customers can use a session token within their account?
Absolutely. So before that, Mark, so first of all, I really like the SDK because the moment you say item request options, I know that it's going to be specific to a specific, it's going to be for a specific request, and I can go change the options at that level. But then Cosmos client options also allows you to basically change options for the entire Cosmos client. And in that case, I could also go and change my consistency level. And that's not something that I would want to do all the time. But, of course, I like it programmatically if I could do it. And then I could go change item request options just to make sure that I know what I'm doing. And a lot of times, the portal lets you pick, but what I've also noticed is some companies, someone else created something in the portal. So it's always better to do programmatically. I don't know if you had any opinions on that.
On the opinions on the what?
On basically doing it programmatically using Cosmos client options. So I could have the consistency done programmatically for the entire Cosmos client instance. And of course, later I could do item request options per request as you needed. But that's basically a one-time thing that I like to do programmatically versus going through the portal.
So you're saying set it at a high level, and then all your instances are at a relaxed level. I don't know if I've heard of customers doing this. I've never really seen it in action, and I don't know how common a pattern that is. I could see people getting into trouble if they forget to set this within their SDK client. But
I think that's required. So you have to set it at the SDK client, But I'll give you examples of customers where I've gone and I'll ask them. So you have an app in production. What's your default consistency level? And you'd be surprised. The answer is no. They don't know. And you go, wait a minute. So because someone set it up, right? Especially big corporations, Fortune 500 clients that I have, and it's like, oh well, we got this from someone else. The entire team that started this, not even on the project. So one of the things I advise them to do is, at the beginning of the app, whenever it is, you basically start with that programmatically, because then you see it in the code, because otherwise you may even forget what you actually had. And then, of course, at the item request options level, you go as you go. And, the example you gave is perfect because I would do the same. Cool.
That's okay. So good point there. And you're right about kind of that, how you could get into that scenario, because we do have a lot of customers who have like entire teams of DevOps folks, and the developers themselves may never have touched that account. They're just given an endpoint and a key by their DevOps person, and then they're like, go use that. Or they may even not have that. They may be using like managed identity or something like that, and they don't know. They've never touched any of that stuff. They just, all they know is there is an endpoint involved. So yeah, that's fair. I'm looking at the slide here. I noticed we have an example for how you get the token when you create an item. I forgot to put a sample in for how you use it when you do a read in there. But we do have documentation on this, and it's not. It's not rocket science. It's not hard to take that session token. It's just a string within there, and then you're just going to pass it in the request in there. So.
The good news is that the session token, especially if you're using the .NET SDK, I don't even think you need to use it because it handles that case for you.
The only time yes, so if you have a single instance of our Cosmos SDK that your customers or your users are connecting through, then yeah, you don't need to manage this at all. It's only if you're running, say, a farm of servers or something, and you've got multiple instances of these things running. And your clients, you don't know which instance your clients are going to connect to in there, because they would not have the same session token information cached within the SDK. So in that case, you want to actually pass that back in the payload back to the end user, and then they can keep that in a cookie or locally, whatever it is you want to do in your client for your customer or your user, and then they pass that back. So
yeah, absolutely. So yeah, I mean, just to talk about session tokens again, right? For those who may have missed this a little bit, I mean, think about this as how do you manage session consistency between your Azure Cosmos DB instance and any of the clients you have, right? So, like for example, going back to my Amazon example, I could go in and put, let's say, my comment. And if there are 400 plus comments over there, I mean, if you go with eventual consistency, no one would even see my comment, fine. But if I go with session consistency, at least I would be seeing my comments. So I see 401 comments, right? Right next, you can have a friend of yours actually look at the same exact comments, might be seeing 400 comments still. Doesn't matter, right? But you at least saw the comment you posted and you're like, okay, I'm good to go. And basically you can leave, right?
Yep.
And in order to make that happen, you have this item response right there, and you get from response that headers a session. You now got that string. And then what you do is you say item request options class, options equals to new that class, and pass in the session token. In this case, we already have the token string, so we'll say session token equals to token. And then, of course, you use container.read item async, pass in the partition key, request options, done, right? So you now can, in just literally one line of code, get that back to your client wherever you are. So you'll never miss the session consistency. That's why it's so much easier than the hack that I talked about. In that case, it worked, but of course I would use this any day. And thanks, Mark, for mentioning that case where it might not be there. So I would always recommend doing this anyways, right? Even though the SDK is handling that for you, just get in the habit of doing this, because just in case there's someone else who takes over your code at one point of time, it's always good to be safe than sorry. And by the way, I was going to add another thing. One of the things I've also noticed with Cosmos DB is it's a QA nightmare. That's why this session is really important, and that's why I was really excited when Mark asked me to join in this session, because if you don't really know what your default consistency level is, well, what do you test for? And that's an interesting thing, right? I mean, one of the things we always do is not just load testing and regular things. You also want to know, wait, you posted something, but is your comment visible? The answer is no, if you're looking for eventual consistency. So what is the QA actually looking for? And that's why it's extremely important to know what that consistency is, not just on the Cosmos client level, but also on the per request basis, because then it's fair for the QA to do their job. Otherwise, there's going to be ambiguity in the response you look for. And sometimes you're going to have fake bugs, which really don't exist, and that's why your use case has to be pretty strong. And based on that, you got to pick the consistency levels.
Agreed. You need to, when you're writing applications using Cosmos, particularly if you're in multiple regions, you should test the consistency model you choose and make sure that you're getting the behavior you expect out of this. It's absolutely right. This is using distributed databases now, right? So you're in a kind of a different world. You're not writing to a single SQL Server instance. You're writing to a database that's actively replicating data in multiple places in multiple regions. So you should test for this and test in multiple regions for this. So definitely more complex. But then when you're building distributed applications, they are kind of by nature more complex, right? It's like the regex expression, right? So I have a problem where I'm trying to parse a string and I decide to use regex. And now I've got two problems, parsing my string and figuring out regex. Distributed systems is kind of the same way. I'm trying to solve for reducing latency for my customers or surviving an outage and higher availability. So I've got those problems. And now I've got a third, which is I'm in the distributed systems world here. So,
and to back to your point earlier, there's always going to be a trade-off, and that's more important to realize than anything else. Is what are we have to have right expectations of what that trade-off was, and we made a calculated decision on what that is. And not that you can't change it down the line, but once you know your use cases very well, you actually save a lot of time, money, effort, and headache not having to redo a lot of that. You'd be surprised. 9 out of 10 clients that we worked with completely ignored, the consistency levels. And not like it's like, like I wouldn't say that it's a blame to anyone, but a lot of time it was like, okay, well, someone else started the project. This went a different way. We're 6 months into it and we realized what it was, and the decisions were taken based on that. And what I say is usually, just look at your business use case. And if you know your business use case really well or get it from the business, well, then it's really easy to pick one of these and then go with it, right? And the next thing I would say is more important is the partitioning strategies. And then you've got indexing, which we have another luncheon, I think, live session coming up in 15 days. We talk about indexing there. So yeah, I mean, it's just very simple things to do and makes your life so much easier down the line.
Yep. All right. We are getting to our very exciting part. We're going to do some exercises here. So there's going to be two parts to this. I'm going to do the exercise that's contained within our lab here. And you can run this out of a VM within the lab environment itself. You can also download this and run it locally on your own machine. Kind of the thing with the lab environments is that they're temporal, so they don't last forever. But if you want to, you can download this code, see this code in action. And by the way, all the exercises for all of the Learn Live sessions are available here. So you can just download or get clone out of there. And then you want to navigate to exercise 21 if you're following along, or if you want to run on this afterwards. There's also another session another set of demos I'm going to show you that I brought into this because it actively kind of shows you the trade-offs here. And so I'm going to run through these, and these are available here from my personal GitHub account. And I promise these will always be here. I will never take them down. And I've been using these and sharing these for, gosh, almost 5 years now in there. So anyway, let's get started. And I'm going to get over to, I'm going to change desktops here. And I'm going to go to this desktop here. And in fact, hold on just a sec. Yeah, okay, we're good.
So Mark, while you're doing this, I was going to say that people don't even need an Azure account for this, right? You get a student account right there when you start the lab, and there's some kind of time limit. Do you want to talk about that?
Right. So when you use the lab environment, you can provision a VM in there, and then that gives you can go and run this exercise, and you don't have to have an Azure subscription at all. You don't need any login or anything. So you can go and create all of these things, not just for this one, but for any of them, using the exercises that are a part of these labs that are within the Microsoft Learn infrastructure here. It's only if you want to run these things on your own or just download the code for them. There's lots of great examples in here, not just for this exercise, but for all of them available within here. Does that answer your question, Chandra?
Absolutely. Yeah. You know, that's what I saw. There was a student account and there was a username and password, and I could easily go on my browser and I didn't have to go create anything at all. And I could just play with it. It was great, even though I have my.
So I'm going to skip by some steps here that are in our exercise because I've gone and pre-created my Cosmos account, and I can show you that. So here's my Cosmos account here. And by the way, I'm going to delete this afterwards. So I don't care what you try to do here. And then I've got my database Cosmic Works. And then I've got a container called products. And that's got a partition key of category ID within here. And then the other thing I want to show you as well is I've set this account up to default to strong consistency in there. And so what we're going to do in this exercise is I'm going to write some data in here. I'll fill in some more code in here, and I've got to get this thing connected to my account. We'll go and run through some code here. We're going to insert some data, and then we're going to do a read on that data with strong consistency, and I'll show you the request charge. And then we'll go ahead and override that. We'll weaken the consistency level to like eventual, and then we'll issue that read again. Okay, so let's get started. First thing I got to do here is I got to get my keys in here, right? So I'm going to copy my keys here. And by the way, folks, I hope this doesn't go without saying, but this is not the most secure way to, oh, whoops, wrong one. This is not the most secure way to do this sort of thing. You should probably be using secrets or using RBAC with AAD or managed identities. There's all these different awesome ways of connecting to Cosmos that don't require the use of a primary master key. That basically just gives you the entire keys of the kingdom there. So, okay. So I got my reference to my Azure Cosmos SDK. I've got my endpoint. I got my key. I'm going to instantiate a new client here. I'm going to get a reference to my products container. And let's see. So I think within there, whoops, hold on. Let me go back to here. Okay, let's go ahead and then I'm going to .NET run this. Oh, sorry, I didn't want to .NET run. I wanted to .NET build it. Ugh, all right, well, this will end quickly. Okay, that was .NET. Whoops, build. I'll go and build that. Okay, that's all good. All right, now I'm gonna add some stuff in here. I got a string ID that I need to create because I'm gonna do a read, and that's pulling something I don't want. And then I'm gonna get my category ID here and pop that in here. And it's still popping stuff in here that I don't want to see. Sorry, I'm copying out of our guide here. So this thing is copying line numbers. All right, now I need to create a reference to my partition key, right? Because I'm going to use that. All right. All right, now I'm going to call my read item async here and get rid of that again. Sorry. Okay, so I got read item async. It's a product, right? And I've got a product class here. And then I'm going to pass in my ID and my partition key. And then let's do a little console action here, and we will print out the request charge. So this is a response.request charge. And then we'll put that in the console right there and then show what that looks like. Okay. All right, so let's do .NET build. That should build okay. Yep, and now .NET run. And then, oh, I got an exception. This is not awesome. Oh, I know what the problem is. I got to put my data in there. Sorry. Hold on. Hold on. I got to put a little record in there. Where are you? All right, here we go. And back to my browser. Whoops. Windows is being a little erratic.
It's also streaming software takes most of your resources.
Yeah, which is why I tend to turn things off like Teams and Outlook and other stuff. Look at this thing. This is not awesome for copying, but we'll get there. Just give me a second.
Yeah, and the good news is that you're copying and pasting from the actual lab, and that's actually very good because you can see how quickly you can learn a concept like this, because we really wanted to give you that same impression of what would it take for you to do it. You just see us do it, and it's that simple. And that's what I did the first time, and I was like, wow, this is pretty cool.
All right, let's see. I think I got a 404 out of there. Build. Whoops, I gotta spell it right. All right, .NET run. Okay, fingers crossed. Demo gods, be with me, please. And there we go.
That's awesome.
So strong request charge is 2 RUs. So remember earlier when I was talking about the request charge, right? For a kilobyte of data or less, it's 1 RU to fetch that data, to read that data. Okay. When you go and read from 2 replicas, double that. Okay. Because each of those replicas had to go and run some compute, your statement here, to go read that data. Okay. So it's double the request charge within there. Okay. So that's awesome sauce there. Now what I want to do is we're going to go in and I'm going to put in my item request here, options. Okay, so back up in here and whoops. Copying is just killing me. And just copy. All right.
So Mark, is it okay if I take a question from the audience?
Yeah, go right ahead while I'm sitting here typing away.
Perfect. Yeah, the question is, when should we use EF SQL versus Cosmos DB?
Oh, Entity Framework?
Realize that you could use Entity Framework Core for even Cosmos DB. So the question is more like, should we use SQL API and EF Core, or is the question, should we use SQL versus Cosmos DB? Just want to make sure I answer the right question.
Yeah, because EF only works with our SQL API.
That's right.
Right. So so you couldn't use Mongo, Gremlin, whatever with Entity Framework. It only works for our SQL API. Now, why would you use it? Well, if you are, I guess if you're migrating from SQL Server and you're using Entity Framework already, that might be an option. It might help reduce the amount of refactoring you've got involved in there. If this is hard. Let me put it this way. I like Entity Framework. I know that .NET developers love it as well, and they use it. Like, I'm an old user of this as well. Using an ORM on a NoSQL database is kind of a weird thing, right? Like, why would you use an ORM when your data is already in the shape you need it? Like, typically, you're going to model your data in the shape you are using it, right? And by the way, you should go see other Learn Lives that talk about modeling and partitioning, because we go into great detail on this. But you're going to save your data the way it's used, so it's already going to be denormalized. It's not, you're not going to store an entity per container in Cosmos DB. Typically, you're going to put multiple entities into the same container, maybe even into the same document, depending on how you need to model the data and how you're using it. So it doesn't make sense. I mean, essentially, and you can see here, like I'm deserializing this data into a product class, right? And here's my product. So it's very simple, right? It's just public record, product, and then ID, name, and category ID. So it's very straightforward, but you can model and deserialize into much more complex objects. Like, say I've got an order or a shopping cart. I can have an order header as an item in here, or I could just say orders, right? And then within there, I got my order header, and then I have an enumerable list, enumerable for all my order details. And I can deserialize directly into that. So there's not, yeah, you could use Entity Framework. It works fine. The support is getting much, much better. Each year, they do a new version of this. I like Entity Framework, and I know our .NET developer community loves it as well. Yes, you can do it. Just keep in mind that there's not 100% fidelity between the two. There are some things that the native SDK does that is not yet available in an Entity Framework. There's also other things that you can do in an Entity Framework that you can't do with using Cosmos. Like, you can't do like the code first or whatever, where it generates the model. That doesn't, or not the model, but the database itself. You can't, that's not supported using Cosmos DB. What I will say is, if performance is your thing and you are trying to eke out the ultimate amount of performance out of your apps using Cosmos, I suggest using or trying our native SDK and building your app that way. And you could compare as well, right? So, and just see what makes sense for you. I hope that answers the question.
Absolutely. I definitely concur, because a lot of times what we've done is taken, a query that's taking like 12 RUs, bring it down to 2 by just using the SQL API. So we like to have the control in our hands, because now I could do a point query with, the partition key, and I could even get 1 RU. And if I'm strong consistency, worst case is 2. But the same query could be taking 12 RUs, right?
Yeah.
So I think I like that control better. I do see the use case where, if you're already on SQL and you think that's easy without having to learn anything. But honestly, going back to Mark's point, if everything is denormalized, everything is JSON, object relational mapper means object and relation mapping. There is no relation here to map, honestly. So I would rather stick with the SQL API any day.
Yeah. So while we were talking, I changed this and implemented my request level consistency reduction to eventual. And here you can see I ran the same exact command, and now that's just a single RU, because it only talked to a single replica within the replica set there. So that's kind of it for the exercise here that's a part of the lab that we're doing. So
Mark,
now
if
I
I
want
were
to
to
show
just,
some. Go ahead.
walk through this for a real quick second, right? Like, so let's just assume that we're developers and, we're not going to do all the security stuff right now. But in terms of lines of code, right, all I had to do was have my endpoint, have my key. I start my Cosmos client right there, and I get the container that I'm talking to. So I got the reference container. In this case, it's Cosmos Works. And, basically I got the entity products. And then all I've really done is create a partition key with that particular category ID. And since we wanted to change it on the request level, we used item request options. If we wanted to do it on the Cosmos client level, we would have gone with line number 6, as you see over there. And line number 16, we said our consistency level is now eventual, means it's going to be the fastest and the cheapest, not necessarily I'm going to get the latest data. But in this case, it really doesn't matter because we're the only ones here. So line number 19, we pass in the request options, as you see over there, and we get the response back. And now we're using 1 RU, whereas it was 2 RUs previously with strong consistency just a minute ago when you had it done. That's pretty cool. So we got through this whole thing in just, I would say, 8-10 lines of code.
Yeah, it's not much, right? These are very simple commands, these types of CRUD operations here. So I want to go on and I want to talk about more CAP theorem, right? And I got some slides that kind of help illustrate the trade-offs in there. And then I want to run a set of demos that I showed you earlier. These are the other ones from my GitHub repo that are basically benchmarks that I run just to show what happens when you make particular choices in terms of consistency within there. So first, let's talk about CAP theorem here. So CAP theorem basically says that you get 2 out of the 3 following guarantees. You get always the most recent data, or always the most recent write or an error, or every request receives a response, even if it's not the latest data, right? It might be a dirty read, or partition tolerance. Your app will continue to work even if the connectivity is lost between the regions here. So in kind of a decision tree format here, you can kind of see this is the choice you've got to make, right? You typically, it's the choices you hear or that you have here really are around availability and consistency. The partition is not really a choice you have. That's really something that's happened to you, I guess, if you will.
Right.
So I can kind of illustrate this, if you will, with a very simple illustration here. In this deployment, I'm going to choose availability for my application. So I have a master replica or a master region here. This is my primary write region. And then I have a read region off to the right-hand side here. So if I choose availability, I write 5 into my account, and then that gets replicated as 5 to my replica. Now, let's assume that I lose connectivity. So this is partition. I have a partition between my regions within here, a network partition, as it's called. So what happens is I write 6 over in my primary write region. However, because I'm opting for availability over consistency, I'm still going to return 5 from my other replica here. Okay, so that's what happens when you choose availability. Now let's flip it. In this scenario, I'm going to choose consistency over availability. So I write 5, and then that gets replicated as 5 over in my other region there. And now I'm going to suffer a network outage, so I cannot replicate data into that second region. And I try to write, what happens? Well, the write is going to fail, right? This is how, this is what the impact is. When you choose that strong consistency, if you cannot replicate into every region in the account, so if you lose connectivity into one of those regions, we're going to reject the write because we cannot provide the consistency guarantee that strong consistency says it provides within there. Now, I want to provide yet another caveat, and this is not something, well, it is in our docs, but it can be rather hard to find. We do have a thing called dynamic global quorum. And what that means is if you maintain 3 or more regions within your account, if you lose one of them, so you have to have 3 at any time. So if you have more than 3, and if you lose one of them, we will still accept writes, and we will temporarily drop out the region that cannot be contacted out of the quorum. So that's kind of what we call our dynamic quorum within there. And if you go and check out our docs on high availability within there, we say a few words in there about how that works and how that can be enabled. So Okay, that's CAP theorem. Let's talk about PAC-LC. So CAP theorem came out, I don't know, about 2000 or something like that. And a guy named Eric Brewer, Dr. Eric Brewer from Berkeley came up with this. And then PAC-LC theorem came along about 10 years later and is an addendum to that. And what that says is, in the case of a network partition in a distributed computer system, one has to choose between A, availability, and C, consistency. But else, if the system's running normally in the absence of partitions, meaning it still replicates, you still have another choice, and that is between latency and consistency. So what does that look like? Well, that kind of completes the picture here. So on the yes side for the partition, that's CAP theorem, and on the right side, that's PAC-LC on there. And that's the choice you have between that latency and that consistency there. So in that sense here, I've got another illustration here. And I'm choosing consistency, which means I'm globally consistent. So I'm using strong consistency here. And what that means is I'm going to write 5 into my master region. I'm going to replicate that over to my other one. Right now, everything is serialized within here, right? So I have to replicate, I have to commit that, replicate it, or commit it and ACK it back to my master and then back to you before that's recognized as globally committed within there. Okay. So yeah, works great. It just adds latency to the requests that happen within there. And you can see kind of by my very slow illustration there. Now let's choose latency in this scenario. So in this scenario, I don't care. I just blast data at my primary write region, and then it will eventually get there because I'm optimizing for latency over consistency in this scenario. So any of the asynchronous consistency models would apply in this scenario. And obviously, the weaker the consistency, the better you're going to do on the latency within there. All right. How are we doing on time? I'm showing 16 after, so I think we're good. Okay, I'm going to show you some demos now. And I'll show you what happens when you make these types of choices in here. So the first one is I have an account that I've deployed. And I'm going to show you 2 scenarios. One is I have a single region, single write region, and that's in the East US 2 region. So you can see that's kind of roughly where, that's probably not really where East US 2 is physically, but it's on the other side of the United States. It's quite a ways away. And I have an app that's deployed both in East US 2, and I also have that app deployed in West US 2 because my thinking is that I want to get my app endpoints as close to my users as possible because I want to reduce that latency. Okay. And so I'll show the single region latency reads from there. And then I'm going to show multi-region latency from within there. So let me now flip over to some demos. And Chandra, can you see what I'm showing here?
Yes, absolutely.
All right. So this is out of that GitHub repo I showed you earlier. I'm going to run benchmark number 1 here, which is single region versus multi-region read latency. Okay. Okay. So what I'm going to do is I'm going to test 100 reads. This is a single master account with a read region both read and write regions are East US 2. So it's a single region account. Okay. And then I'm going to test that from my app that sits in West US 2. Okay. So let's see, what is that latency like? And getting somewhere in the low 70s to 60s milliseconds, average about 60 milliseconds for each of those, which is about what the latency is on the WAN, on Azure WAN, from one side of the US coast to the other. So from West US to East US. Okay, now let's try this again. This account has a write region East US 2 and a read region in West US 2, which is where my app that's running this benchmark is running. Now, Chandra, what do you think? Is this going to be faster or slower or the same?
So we're in the same region. Of course, it's going to be way faster.
Yeah, let's see what happens.
And the throughput is going to be the same.
How's that for fast?
Wow, look at that.
So, I mean, yeah. So beautiful. Look at we advertise 10 milliseconds, less than 10 milliseconds at P99. I think that's over a longer period of time, or maybe it's in an hour. I don't remember exactly what our SLA is, but what I want to show you is that like the P50 for this is like into the 4 or 5 millisecond range here, right? I think I even saw some smaller.
I mean, really try the median. That's probably 4 or 5.
Yeah. So, and you can see there's a couple of ones that hiccup more here. Usually the first of them are the slower ones because they're just getting started, and then they go real fast from there. And here you can see, I mean, my average was 5 milliseconds. So if I compare this to if I'm in West US and having to go all the way across the US to read every line of data or any record out of my database, that's 68 milliseconds, nearly 70 milliseconds of latency that I'm taking a hit on. May not be much for you, but lots of apps are latency sensitive and they want the data as fast as possible. So replicate that data to the region where your application sits, and then it doesn't have to go very far to get that data. Not only is the request to the database faster, but the entire experience is faster, right? It's the lower the latency, the higher the performance, right? These are directly inversely related to each other. Latency is performance. Okay, so that is that one. I want to show you, I'm going to do another slide here and show you another demo. And I'm going to show latency for reads and writes that happens within here. And I'm going to enable something, well, we call it multi-master. It's actually multi-region writes is what we call that today. And what that does is that makes every one of the satellite regions writable, right? And so how that works is that you write data into that region, and then it goes to the primary and then gets merged and then gets replicated back out, okay? And then every one of those regional endpoints can now accept writes in there. And you're going to get that same low latency within there for your writes. So let's show what that looks like when I'm comparing performance for a single region write versus multi-region write within here. And so I'm going to run test number 2. Okay, so I'm going to test 100 reads, single master account with the read region of West US 2 from West US 2. So this is going to be, what do you think, Chandra?
So it's from West US 2 to West US 2 single read. That's going to be really fast.
Yes. Boom. There we go. 6 milliseconds that time. Very good. Now let's test 100 writes. So I'm going to be writing from my app in West US 2 to my single region write account, and that single region account sits in East, or the write region sits in East US 2. How is this going to be? Fast or slow?
Definitely slower.
Yeah, right. Because I got to go all the way across the US for those writes that happen within there, right? So now we're back up into our 60, 70 millisecond range, right? Which again is like that. That's really the average in there for getting across the continental US. Okay, this account is configured for multi-region write for their multi-master, and we're going to test 100 reads. And multi-region works the same as the other. I'm replicating locally or into that same region, so I'm going to get fast speeds for my reads, of course, right? Because that's going to work just the same as it does when I replicate using a single region write account. Now I want to test 100 writes into my multi-master configured account from West US 2 into West US 2. Chandra, thoughts? Fast, slow, same?
Definitely better than the previous one.
You bet. Way fast, right? So 6 millisecond latency within there. One thing I want to point out is
the throughput.
Using
what's going on with the throughput on that?
Yeah, so using multi-master incurs additional throughput cost within there. So that's something you have to keep an eye on, is when you use this configuration, yes, you get very low write latency from any region, but you will incur expense on the writes that happen within there. So again, this is information that's important to understand and to know as you're planning your application and testing it in here, is the behavior of the service, depending on the configuration within there. So there you can see, yes, multi-master is good from a latency perspective, but it does come with cost that's available within there. So just another thing to keep an eye on. Okay, one last, or maybe a couple of slides here just to show, where am I going? Okay. All right. So next, I want to show, whoops, wrong ones. Yeah, these are the slides I was showing earlier. All right. Here's my last test. I'm going to show this is a PAC-LC demo. Okay. And I'm going to show the trade-offs of latency versus consistency. I'll also show the consistency versus throughput This is part of another demo where I showed that as well, but we kind of already showed that earlier. So how this is going to work is I've got an account set up using eventual consistency. I've got a region, my write region is in West US 2, and I have a read region, secondary replicated region in Central US. So about 1,000 miles. And then next, I'm going to do the same thing, same layout, but this account is configured for strong consistency. Okay, so we'll have to see what happens to our impact in terms of the latency for our writes within there. I'm then going to do something kind of fun, and I'm going to double the distance between the regions. So Central US, about halfway between the West and the East Coast, at least that region is. Why don't we see what happens when we do strong consistency, and we just double the distance. Let's see what happens to our numbers in there. And then I'll show you throughput cost with eventual and then strong. But I think you already have seen that, of course. So that's okay. All right, going back to here. All right, here we go. I'm going to run benchmark number 3, consistency versus latency within here. And so I'm going to test 100 writes, eventual consistency, writing into West US 2 and replicating to Central US. What do you think? Is this going to be fast or slow, Chander?
So eventual is going to be way faster.
All right, let's see what happens. So you bet. Eventual consistency, writing into the region I'm in, into the same region, it will be very fast, right? So you got on average 7 milliseconds here. Yep, that looks pretty good. All right. Well, let's try it again. Same test, 100 writes, West US 2, Central US, configured for strong consistency. What do you think?
Slower than eventual.
Right, serialized. So there you go. If you notice, my latency here is about what I experienced with the reads. The reason is because that whole thing had to do a round trip. So it's basically like going across the whole US. Right?
Totally.
So I had to write it and then I had to act back before I could.
But you're getting the latest, in case, version of that document. So you're paying that price, which is perfectly exactly what we talked about in the.
That's right. Yeah. That's the trade-off, right? If perfectly consistent data, RPO 0, and by the way, I don't know if people realize this, but our consistency models are essentially a dial on RPO, right? If you have a business requirement of RPO 0, I cannot ever lose data in the event of a regional failure or some kind of failure, then you have to use strong consistency. But you must acknowledge the trade-off in write latency that comes with it, okay? And so, yes, you're going to pay a hit on the right path to get perfectly consistent data. All right, now let's try this. So I'm going to double the distance between these regions. And Chander, what do you think? What's going to happen to my latency here, do you think?
It's going to slow down.
How much do you think?
So you got a double round trip there, right? So whatever is that number, I don't know.
All right, well, I can say this. If I double my distance, what do you does it double my latency, do you think? Let's see what happens.
Yeah.
And pretty close.
Double, because it's 0.7% of what is it, like speed of light, I guess. So
yeah, almost double.
Yeah.
And there it's not Central US to East US 2 is not.
Well, let's put it this way: the worst case is double, I think. It doesn't necessarily have to be double because of the constant we have that I'm forgetting right now. But
all right, I'm running out of time. I think we got to go. So that's 1 RU, and then measuring strong 2 RU. So there we go. I think we're nearly out of time here, Chander. What is? Oh yeah, I'm hearing 90 seconds. Okay, folks, we're gonna blast right past our knowledge check, but please feel free to take those knowledge checks when you take the lab here, and then. Summary. So we've talked about configuring consistency for Cosmos DB account and then changing that consistency on a request basis. Definitely for more information, check out our Learn Live here. We really want you to take and consume all of this content that's within there. And then, complete the interactive learning, watch the videos, practice, right? All that stuff. Download from GitHub all of our exercises and play with that in your own subscription if you want. And hold on, I got one more slide. Hopefully we can make it. More stuff coming up, so feel free to take a screen cap of that. And I think we're nearly there. 30 seconds. So I guess this is it. We say goodbye, Chander. It was great. doing this session with you today. Like I said, this is one of the reasons I love and work on this team is distributed database is just good geeky fun. It's anything distributed systems is just kind of a it just turns my ear. I love it. So, and it was great having you as a partner this time on.
Well, thank you. I mean, I love the consistency levels. I love the guarantees. I love the fact it's 5 nines. I mean, this is the best it gets. What a great product. Thanks for the great product you built.
You bet. Thank you, sir. And thank you everyone for joining us. We'll see you next time.
Thanks everyone.
Bye-bye.
So good to join you here.